In my previous installment, I talked about biofuels and my desire to explore third-generation biofuels derived from algae. One such fuel is known as biodiesel, and it's fairly easy to make, and more people are bound to be interested in it because of the rising fuel and energy costs we currently face. So because of this, I thought it would be useful of me to show people the ropes on how to make their own biodiesel. Additionally, I want to explore the preparation of some exotic biodiesels that use different alcohols in their manufacture. Because I am currently unable to cultivate algae beyond the demonstration scale in order to extract the lipids from it, in lieu of such, today for this experiment, I am using vegetable oil. Fats and oils are what's known as lipids, and they are primarily composed of chemical compounds known as triglycerides. These are compounds consisting of a glycerol molecule attached to either 2 or 3 long-chain fatty acids. Vegetable oil can already be used as a fuel, but it has the drawbacks of having high viscosity and high ignition temperature, which make it not as good as a fuel for diesel engines. In the biodiesel production process, the glycerol molecule is instead replaced with a short-chain alcohol, and this decreases the viscosity and also the ignition temperature and makes it a better fuel. It also forms glycerol as a byproduct, which has many uses of its own. For this experiment, I have 3 alcohols at my disposal: methanol, ethanol or ethyl alcohol, which is drinking alcohol, this is denatured alcohol, and isopropanol or rubbing alcohol. Methanol is most commonly used for making biodiesel because it makes the most efficient fuel and is also the easiest to make. However, I'm interested particularly in ethanol to make biodiesel, because if we can use ethanol to make biodiesel, it would mean that we can make the biodiesel production process completely renewable and sustainable. However, the thing is, we can't just mix oil and alcohol and Bob's your uncle, we have biodiesel. No, we need something else that can help drive the reaction along. This is known as a catalyst. Now, normally when people make biodiesel, they tend to use this stuff. This is sodium hydroxide or lye. Now, this works perfectly fine for when you're using methanol. However, the reaction is quite slow, and you can't really use sodium hydroxide to make biodiesel from other alcohols, because it simply isn't basic enough. You probably could get some biodiesel by using sodium hydroxide to make ethanol biodiesel, but the reaction would be very slow, and you'd get quite a low yield, and a lot of soap. The reason why sodium hydroxide isn't basic enough to deprotonate higher alcohols than methanol, which is basically to remove a hydrogen atom from the alcohol, is because the sodium atom is quite small, and so it holds on to its hydroxyl group, its OH group, quite strongly. So what can we do about this? How can we make different biodiesels, such as from ethanol, with lower reaction times and with higher yield? Well, instead of sodium hydroxide, something else we can use, which I have here, is potassium hydroxide. Now, potassium hydroxide is actually more basic than sodium hydroxide because it has a larger atom. Well, the potassium atom is larger, and so the OH group, the hydroxide group, is able to dissociate more easily. Now, if you're familiar with pKa values, you'll know that as the temperature of a mixture increases, its pKa value decreases. It becomes more acidic, and this makes the base easier to react with the alcohol, which in this case acts as the acid. And basically what this does is this forms things called alkoxide ions, such as methoxide, ethoxide, etc. And these are able to react with the lipids, the triglycerides, and convert them into biodiesel. While methanol is toxic by ingestion, it is also quite harmful by inhalation exposure. Thus, this experiment is going to be done outside, in an open air environment. I'm also going to be wearing some gloves to prevent dermal exposure. Anyway, let's get to it. Also be aware that alkali solutions are corrosive, especially when hot. Now we're outside, and what I have set up here is something called a Buchner funnel and a Buchner flask that's connected up to a vacuum pump. And what I have inside of here is my methanol, which I have dried using some anhydrous magnesium sulfate. And you can get magnesium sulfate and the anhydrous version by simply cooking some Epsom salt in the oven for an hour or so. So I've got my filter wet with methanol, and now what I'm going to do is I'm just going to pour the rest of this in and filter off the magnesium sulfate using my vacuum pump. So now we turn on the pump and you should see liquid start to appear in the flask. And that should be a lot clearer than what we have here. And here we have some residual magnesium sulfate crystals after filtering, and we can use these later in another drying process. Now this is what the methanol looks like. It's still a bit cloudy, so what we'll need to do is we'll need to go grab another paper filter and paper filter this through a gravity funnel. So here we have our methanol that's almost done gravity filtering, and let me just stress that it's really important for biodiesel production that you dry your alcohol. If you don't dry your alcohol, basically it will slow down the reaction a lot, and your chances are that you'll get basically a load of soap, and that's, in this case, that's pretty undesirable. So in order to avoid that, you want to make sure that your alcohol is as dry as possible. I use magnesium sulfate. You can use the sieves silica gel, but you just need to make sure that it's dry. Same case with your oil. I pre-dried that with calcium chloride, and that's the oil I'm going to be using today. Okay, so the next step is to weigh out and add our catalyst. So I have 2.79 grams of potassium hydroxide here. I'm going to add that to our flask and stir it until it dissolves. As you can see now, that's stirring away with my magnetic stir bar, and we'll give that a while and wait for it to fully dissolve before adding our oil. In aid of this, I'm also going to turn the heat up to about 50 degrees, and that will dissolve it further, and that will also prep it more for our reaction. I guess this would be a good time to mention that the theoretical ideal scenario for this reaction is that you have 10 parts oil and 1 part alcohol. That is, you have a 10-to-1 ratio of alcohol to oil. However, I have about 100 mils of oil there, and I have about 30 milliliters of alcohol, in this case methanol, and what that means is that I have an excess, which should improve yields a fair bit. Something I'm just doing quickly now, I've taken that off the heat and the stirring, and now what I'm doing is I'm basically letting my oil sit on the hot plate to warm up a bit, and this will aid the rate of the reaction. Now, as you can see, our potassium hydroxide has completely dissolved in our methanol, and it looks a bit cloudy, but that's okay usually. Now that our temperature is closely approaching our target temperature of 60 C, we can now begin to add the oil. What to do is turn up the stirring by a whole lot so that the two layers begin to mix. And that should start the reaction. What should be happening here is a reaction known as transesterification, where one alcohol is swapped for another alcohol on a acid substrate, a carboxylic acid substrate, and that generates a different ester. Now, transesterification is quite a slow process, so this is going to take a few hours. But by that time, out here it's going to be probably a bit dark, so I will see you inside with the results. Oh, just something important to note. One thing is that ideally you would be doing this at a higher temperature under reflux, so about 70°C with a reflux, which is, I think, is what another YouTuber did by the name of Chemiolis. He did a biodiesel video himself. And also, you may be wondering why I have aluminium foil wrapped around the flask, and that is because it's cold outside and the aluminium foil helps insulate the flask and keep heating. Now, while that reaction is running, we're going to prep our ethanol for when we try the ethanol transesterification. So what I have here is some 190 proof Everclear, and I have about a spoonful of magnesium anhydrous magnesium sulfate in there, and I'm just going to pour some of our Everclear into there, and I'm going to close it off. I'm going to let it dry. That should be enough. Now, the thing with ethanol is that it's quite different from methanol in that it takes a lot longer to dry. Well, not really a lot longer to dry. I guess it takes a lot longer to dry, but it's very hygroscopic, ethanol is, and so it's very difficult to get it fully dry. It absorbs moisture quite easily. So literally as soon as we filter off the magnesium sulfate, we will need to use this. And also we need to use more magnesium sulfate to dry this than we would if we was drying methanol. Then, as I've shut that off, I'm going to give that a shake. Leave it for about 24 hours, and then we should have some dry ethanol. I've also done a similar thing with another 100 milliliters of oil as well. I've got some of my anhydrous magnesium sulfate in there, and I'm going to just, shake that around and leave that overnight, and hopefully tomorrow that should be dry. So after about 2 hours on the hot plate, this is what we have. Now, because I didn't reflux it, a lot of the methanol is likely to have already evaporated. But now all I have to do is wait for the layers to separate, and that should take about in between 4 and 8 hours according to Google. So I'll be back tomorrow to see if this has separated into the biodiesel and the glycerin layer. So here we are back inside, and the layers didn't actually separate too well. And so what I did was I transferred most of it to a separatory funnel and added a non-polar solvent, in this case pentane, and then I went and neutralized the base, the potassium hydroxide, with a dilute solution of citric acid. And acidifying it essentially broke any soaps, and it neutralized the base, and it allowed for greater separation. And as you can see, it's clearly separated into 2 layers. Now at the top layer we have our less dense biodiesel layer. It still has a pentane in it, which was used for the extraction, and in the bottom layer we have our glycerol layer, which is contaminated with methanol, water and citric acid. And so what we're going to do now is separate these and do some more work up from there. So now that we've separated our 2 layers, we need to do some workup on them. For the biodiesel, what we need to do is we need to evaporate off, or we need to strip all of the pentane. And we'll do this through a simple distillation. So after a few days and a little bit of research, I found that I kind of screwed up. So what we have here is our biodiesel layer that I've stored in this bottle, and this really isn't good quality biodiesel, and the reason for that is because of the methods I used. This, you can see here, it's quite a dark colour. Biodiesel itself is supposed to be rather pale, and the reason for that is because of something that I did, where I actually used too much base, too much soluble base, so like too much potassium hydroxide, and that led to the formation of an emulsion of biodiesel, glycerin and soap, which is what we have in this bottle. So I'm going to try the synthesis again and see if things improve. After reading up on some recipes online, I found that I was using exponentially more base than was necessary. A theoretically ideal biodiesel recipe is to use a ratio of 1 to 10 in terms of your alcohol to oil ratio. That is, for every 10 parts of oil, you add 1 part of alcohol. And ideally also, you want to use about 0.5% of your weight in oil in base. So that would mean that if you're using a sodium hydroxide, you would want to use about 5 grams for every litre. And since potassium hydroxide is 1.4 times less dense, you would need 1.4 times more, which is about 7 grams per litre or so. Now, because I'm doing this on a small scale, about 100 millilitres, I have to divide that by 10, which means that for this recipe, I'm going to be using about 0.7 grams, ideally, of potassium hydroxide. I may add a slight excess, about 0.8, 0.9, perhaps 1 gram, in order to ensure the completion of the reaction. I don't want to make the mistake I made before, where I added too much potassium hydroxide, and thus what happened was I ended up with a bunch of soap along with a very low yield of biodiesel. So we're going to go back outside now and test it out. Oh, and for anyone curious as to why adding too much base can just produce a load of soap instead of biodiesel, is because as the transesterification reaction progresses, it creates more water, which forms a solution with the potassium hydroxide, and thus starts to saponify the oil instead of transesterify it, which is unideal. Anyway, let's get back outside and see if we can actually make some biodiesel. So to start off, what we're doing is we're warming up our oil. This will remove any moisture and will also serve as a way of speeding up the reaction. I have my hot plate set to a target temperature of 90 degrees, and this should warm up the oil enough so that when it cools down, it will cool down to a temperature suitable for transesterification, whilst we prepare our catalyst. Moisture shouldn't really be an issue here anyway, as I've pre-dried this oil with some anhydrous magnesium sulfate. While that's warming up, something I thought I'd do is go and prepare my condenser, as today I'm going to be refluxing. This should keep any methanol in the reaction flask and optimise the yield. All this is a couple of tubes hooked up to a Liebig condenser, which is hooked up to a submersion pump, which is in a bucket of water. Something I've done to dry my methanol is I've actually added some anhydrous magnesium sulfate to the bottle, and what this does is it eliminates the need to dry individual batches, and thus makes for an easier process. However, something I need to do is I need to let this settle to the bottom so that I don't get too much magnesium sulfate in the reaction itself. However, a downside to doing this is that before I do any reaction, I need to let the magnesium sulfate settle to the bottom in order to prevent it contaminating the reaction vessel. I've got 0.93 or 0.95 grams of potassium hydroxide, and that's going to go into my reaction flask now. Got my stir bar in there with the potassium hydroxide. I'm just going to top that off now with 20 milliliters of my dried methanol. So here you can see it on the hot plate now, and I'm just going to let that stir and heat up until all of the potassium hydroxide dissolves in the methanol, and we reach our target temperature of 60 degrees. Now that our methanol hydroxide solution has almost reached target temperature, what I'm going to do now is add our oil. I'm going to add our condenser, and I'm going to turn on the cooling. And now we have our reaction going. We're almost at target temperature again, and now I'm going to leave this for a couple of hours while the transesterification takes place. As you can see here, we have our reflux condenser. Well, it's a Liebig condenser, but I'm using it for reflux, and that should keep any methanol in the reaction flask. So I'll be back in a couple of hours, and we will see our results. So after about 2 hours of stirring and heating, this is what our mixture looks like. It is currently homogeneous, but over time it will separate into the biodiesel layer at the top and the glycerin layer at the bottom. So here we have our two layers in the separatory funnel, and that didn't take as long as I thought it would. It took about an hour actually, rather than 4 hours. So now what I'm going to do is I'm going to decant these into two separate containers, and we'll deal with them separately. So with our biodiesel layer, what we need to do is we just need to wash it and dry it, and then it should be ready for testing. With our glycerin layer, what we need to do with that is we need to strip it of excess methanol, and we need to purify it, and then it should be a clear, viscous liquid that is indicative of pure glycerin, or glycerol as some call it. So into our flask goes our glycerin layer. And we are left with our biodiesel, which we're going to drain off into a separate container. And there our biodiesel goes. What I've actually done is I've put the glycerin layer back into the separatory funnel, because what we can do is we can use an extraction solvent, in this case pentane again, to extract a little bit more out of our glycerin layer. So we're going to add some pentane here. What we need to do is stopper that off and give it a bit of a shake. And we drain off our layers again. So here we have our two fully separated layers. We have our tiny glycerol layer here, which is contaminated with methanol and some other stuff. And we have some biodiesel here, 100 millilitres of it in fact, that we need to strip the pentane off of, and we need to dry. So off camera I washed my biodiesel using some phosphoric acid and water, and now what's happening is I'm just drying it over some more anhydrous magnesium sulfate, and hopefully when I filter it off it should become clear. So what we're doing now is we're just gravity filtering our biodiesel, and once this is done I may need to filter this again in order to get it to a higher purity. As you can see, it's coming through the filter quite clear, and in the background you can see a colour comparison. That is just a beaker filled with 20 millilitres of oil, and you can see that the colour is quite similar, which indicates a low conversion rate. Something I could do in the future is run this through again and get some more biodiesel out of it, but for now this will suffice. You know what? I have a feeling I'm still not going to be quite satisfied with this. I'm going to do another run, aren't I? So, what we have here definitely qualifies as biodiesel, but it's not the highest quality. I mean, we saw it was biodiesel. I mean, we have our glycerol layer here to prove it, but I think we don't have complete conversion of the of the triglycerides to the methyl esters. So what we can actually do is we can reprocess this. We can take our biodiesel here and we can actually go through the process of further transesterification, and that will lead to more conversion into the methyl ester instead of because this is currently a solution, in fact, of it's a solution of vegetable oil in methyl ester, and what we want is more methyl ester and less vegetable oil. If we run this again with some more methanol and some more KOH, it will actually lead to a higher conversion of triglycerides into methyl esters. So what I'm doing here is I've taken our biodiesel that we made in the first run and I'm giving it a second run with some fresh methanol and KOH. I'm using a slightly less amount of KOH, about 0.7 grams instead of 0.95, and I'm using the same amount of methanol, and that should give us a higher yield and a higher conversion of the triglycerides into the methyl esters that we want. So I'm going to leave that now at about 50 degrees for about a few hours, and I am doing this inside, which means I need to take a few more precautions since we're working with methanol. Firstly, I've set the target temperature below methanol's boiling point, which should prevent a lot of the vapors from escaping, and also in aid of that, I have our condenser, which isn't circulating but is still filled with water, and that should condense any vapors that evolve from the mixture. And I also in the background have adequate ventilation measures in place. So I'm going to leave this for a few hours and see if we get any more conversion of our biodiesel. Okay, so my attempt at improving the biodiesel by trying to increase the concentration of fatty acid methyl esters didn't really quite work. I think I used too much base, even like by a little bit, and I ended up with a homogeneous mixture again, which I had to try and separate, and in doing so via acidification, and when I acidified it, I ended up inadvertently hydrolyzing some of my product, which obviously isn't good because it will decrease the yield significantly. Anyway, if you want to make really high quality biodiesel, it's best to do it all in one stage and for an extended period of time in order to ensure complete conversion. But I'm going to stop here because I don't want to lose any more of my product. So right now I'm doing another run, and what I'm doing this time is using slightly less catalyst at about 0.7 grams instead of 0.9 grams, and I'm going to run this at a target temperature of 56°C for 3 hours, and hopefully, as opposed to the 2 hours from my previous run, this should increase the yield and the purity of the biodiesel quite significantly, and a greater percentage of our mixture should be methyl esters instead of triglycerides. So I'll be back in a few hours and we'll see if this yields a better result than the lower grade biodiesel I produced last time. While our second batch is being produced, I thought I would go ahead and dry our first batch with some anhydrous magnesium sulfate, and now our first batch of biodiesel is just filtering off now, and as you can see it's coming out quite clear. So it's been about 3 hours now, and as you can see our mixture has changed colour quite significantly. Now what I'm going to do now, since the reaction is most likely finished, I'm going to take it off the heat and take it off the hot plate and disassemble the apparatus, and then we will allow the mixture to separate. And as you can see it already separates fairly easily. You can see the glycerol starting to fall down. If I put this on the desk it may separate even better since I'm not agitating it. You can see the glycerin slowly start to fall down to the bottom and accumulate there, and on the top layer will be our biodiesel. Our second batch of biodiesel. You might be able to see it a little bit better at an angle here. As you can see, it's really starting to separate now quite fast. Anyway, I'm going to leave this to separate fully, and then probably when I get time, I will further process this. Here we have our 3-hour biodiesel. I still haven't drained off the glycerol layer yet, but as you can see, if we compare it to our 2-hour biodiesel, this is quite yellow, and this is surprisingly a lot paler, and that indicates that we have made a much higher quality product. Anyway, I'm going to go ahead and separate these two fractions now, and we might be able to see the actual colour of our biodiesel a little bit better. So I've just separated these fractions the best I can, and we can already see the benefits of leaving the transesterification process for a little longer. That is a lot paler than that, and I bet you that right there is a lot higher quality. And we have our glycerol there looking very dark red. There's still some residual biodiesel there, but that's not too much. So all I need to do now is I need to wash this, I need to dry it, and it'll be even purer. And after I've dealt with the biodiesel, we will come back to our glycerin fractions, the one we've produced now and the one we produced earlier in our first reaction. So our water goes in. Now that is some very wet biodiesel. I think it's sulfate time. And now that's just filtering through. So here is our final product, and would you look at that purity, it is almost colourless. In real life it still has some colour to it, you can't really see it on the camera, but it's still a lot better than what we produced earlier. And I'm actually quite proud of what we've accomplished here. To give a comparison, here is some regular vegetable oil, and here is our biodiesel. And as you can see, there is a stark difference in the colour, which definitely indicates that there has been a lot of conversion from the triglycerides in the oil to the esters in the biodiesel. What I've actually done is I've gone and run the maths on this, and here we have about 80 millilitres, or give or take, of biodiesel. And assuming your average 44 mile per gallon diesel car, this will get you as far as about 3/4 of a mile, so I've calculated. Which, even though that's not far, I still think that's quite impressive for what we've produced essentially in a home environment. Since we now have our biodiesel, we can proceed with recovering our glycerol. Here I have our glycerol fractions from our previous reactions, and what we're going to do is first we're going to strip the methanol via simple distillation, which is what I'm currently doing here. And we're currently at 64.5 degrees, and our methanol is starting to bubble, and we're starting to collect some drops of liquid in our receiving container. So from our distillation, we've obtained about 10 or so millilitres of methanol, which we've recovered from our mixture. And this is quite impure. I will have to redistill it again before using it for a potential future run. Okay, so what we have here is a couple of things. We have our crude glycerin that's also contaminated with some jellified biodiesel. Now the first thing we need to do is we need to destroy that biodiesel via acidifying it. So what we have here is just a dilute phosphoric acid solution. As you can see, it's quite acidic, as it should be. And all we're going to do is we're going to acidify our mixture here, and hopefully that should destroy our gelled biodiesel. To attempt to aid the hydrolysis process, I've gone ahead and transferred this to a larger beaker, added some water, and I've just put it on high heat and high stirring, and we'll see if this aids in the hydrolysis. So after some pretty thorough convincing through some heavy stirring and some heating, we can see that most of the biodiesel has been destroyed. And now what we need to do is we need to re-basify the solution with some baking soda. You can hear that fizz, you can hear it reacting with the phosphoric acid, and that should be neutralising the pH in this mixture. Also, slight oversight by me, you should really try to prevent this from happening. The solution was still quite hot, and when I added the bicarb, it just kind of boiled over. So unfortunately, because of foaming, I lost quite a lot of liquid. But now that we have a neutral pH, I'm going to try and filter this and see if there's any glycerin in there. So because of that failure, and because I had so little liquid left, I changed my mind and decided that it wasn't worth extracting the glycerol from it. So what I'm going to do now is something which could actually solve a big problem with biodiesel, and that is the fact that it uses methanol, which is somewhat toxic and isn't easily obtainable by most people. Making biodiesel with ethanol would prove much more sustainable than using methanol, as both the vegetable oils and the carbohydrates necessary for the ethanol can be grown naturally rather than be derived from petroleum-based products. The main difficulty with using ethanol as opposed to methanol is that ethanol is much more hygroscopic. On top of being hygroscopic, something related to that is the fact that at about 96.5% concentration, ethanol forms a stable azeotrope. That means if you try to distill it over 96.5%, it will try to form the azeotrope again with water. And this makes the biodiesel production process with ethanol much more difficult, because you really don't want water in your reaction, as that can form soaps and other byproducts. And so that's something that's been under investigation for quite a lot of time. So in order for me to do this, I need to make sure that all my reagents and all my glassware are 100% dry. So I've been drying this ethanol now for quite a while using magnesium sulfate. I'm just drying my oil here, about just under 150 milliliters, with magnesium sulfate as well. So off camera, I measured out 40 milliliters of dry ethanol, dried with magnesium sulfate, and I'm filtering it directly into the reaction flask. It will minimize contact between the moist air and the ethanol, and will give less opportunities for the ethanol to reabsorb water and form the azeotrope. Because I have about 150 milliliters of oil to transterify, I'm using about 1.3 grams of potassium hydroxide for this reaction. Off camera, I added the potassium hydroxide flakes and then reattached the funnel ready for the filtration of the oil directly into the flask as well. I'm going to let this heat up and let the potassium hydroxide dissolve into the ethanol. Target temperature for this process is 70°C, and this is a perk of using ethanol for biodiesel production, because you can crank the temperature a little bit higher and thus you'll have a faster reaction. Another perk of ethanol-based biodiesel production is that the process is almost entirely non-toxic, so I could even perform this process inside without much issue. Anyway, I think it's time for us to start adding our oil and get this reaction going. So I'm just filtering this directly into the reaction flask through a paper filter. Okay, so plan B, I'm using a little bit of tissue as a cotton plug. So let's see if that works. In the end, I decided to just dump in all of the oil because the magnesium sulfate impurity probably won't affect this much. In fact, it might even serve as a mild water scavenger. What I'm going to do is I'm going to let this sit and react for a few hours, and I'm going to come back and see if we have successfully made biodiesel from ethanol. So to my surprise, it actually worked. After about 5 hours of reaction time and some filtering to remove the sulfate, we have our biodiesel made from ethanol. So here in this jug we have the majority of our ethanol biodiesel. It's still quite crude. I might end up actually reprocessing it or trying to. And in here we have two layers of biodiesel and glycerol. And what I'm actually going to do with this is I'm going to perform a pentane extraction to hopefully prevent the gel formation that we had with the other batch. And the reason I want to reprocess this is A, to make a better biodiesel, and 2, to extract more glycerin. And what I'm going to do with this after I've performed the pentane extraction is I'm going to go through the process of washing and drying both biodiesel fractions, like up there and here. From there, I will try to give this a second transesterification step to see if we can get the most out of our reagents. After the pentane extraction, the biodiesel and glycerin layers are much more well defined, which consequently should make them easier to separate, which is what I'm going to do now. And now that the layers are separated, all I need to do now is I have some water in there, and now I'm just going to wash the biodiesel and dry it. While the water washing separates from the biodiesel, I've prepared another batch of anhydrous ethanol. So here is after washing and drying the ethanol biodiesel, and it still has a fair bit of yellow colour in it, which indicates the presence of, which indicates that there's still a presence of triglycerides in there. And so what I'm going to do is I'm going to try and successfully complete a 2-step biodiesel process via giving this another run and seeing if I can make this have a much higher ester content than it already does. So what I'm doing now is a cleaner method of drying oil and biodiesel, which is rather than use magnesium sulfate, I'm basically just heating it up to a high temperature above the boiling point of water, and this should dry it sufficiently and should also ensure that we have a dry reaction vessel. Since we use some pentane for the extraction steps, all of our pentane, or most of it, should distill over as well, so that we can recover it for later use. I have a stir bar in there with minimal stirring speed on, and basically that serves the purpose of regulating boiling and making the boiling of the pentane and any other volatiles much less erratic and violent, so things should be much more steady. The boiling point of pentane is about 36 degrees centigrade. We are currently at a temperature of 41 degrees centigrade, and nothing has came over into our receiving container. What likely happened is that between processing steps, all of the pentane has just evaporated off. I mean, it's quite volatile anyway, so that's to be expected. And on top of that, our biodiesel is pretty clear, which indicates it is already quite dry. So I think we are ready to move on to our next step. So in this beaker I have about 0.4 grams of potassium hydroxide, and that is quite conservative However, what I'm trying to do is prevent the oversaponification of the biodiesel in this two-step process, which was a problem in our previous attempt at a two-step process. And what I'm doing now is, in order to minimize steps and therefore minimize the amount of contact ethanol has with the air, and thus minimizing the opportunity for the ethanol to form an azeotrope with water, what I'm doing is I'm filtering our magnesium sulfate dried ethanol, about 20 milliliters of it, directly onto our 0.4 grams of KOH, so that it can be ready for our second transesterification process. So with a bit of haste, I'm now preparing our catalyst using some stirring and some heating to try and get the KOH to dissolve in the ethanol before it forms a azeotrope, and then we can get on to the main reaction for our two-step process. Right, so now that our catalyst is mostly dissolved in our ethanol, we can now heat up our oil, or biodiesel now, to about 65 degrees C, and then when it reaches that target temperature, we're going to add our ethanol with our catalyst in it, and we're going to see if we can get a better biodiesel out of this. So in goes our catalyst. We're at about 66 degrees C. So it's been almost 2 hours now. I'm going to stop the stirring and turn off the heating, and I'm going to let that settle and cool down, and hopefully it will separate into 2 layers. So after 2 hours, we do have 2 layers here, but the thing is, it's different this time, in that the upper layer it's very thin, you can't really see it that well, but that is actually our, well, it's supposed to be our glycerin layer, and it's on the top, because I think that there isn't that much glycerin in there, and the density of ethanol is less than that of biodiesel. So I think there is still a tiny amount of glycerin inside there, that layer, but not a whole lot that would, not enough to cause it to form a layer at the bottom. The rest is biodiesel, and it's looking like the colour hasn't changed that much. So I'm going to separate this, I'm going to clean and dry the biodiesel, and I'll get back to you. So after washing and drying, here is our ethyl ester, and I only have about 75 mils of it. Losses were primarily due to clumsiness, filtering, parts of our yield soaking into the like filter paper and stuff like that. But nevertheless, we have some ethyl ester biodiesel here. Now here we have our glycerin layer, which we saved before, and I'm going to try a second attempt at purifying this so that we can get some pure glycerin. Now, as with the first attempt, a prerequisite for extracting pure glycerol from this mixture is to hydrolyze any remaining biodiesel and soaps. And we do that via adding a strong acid. The last time I used a dilute acid and I neutralized it for some reason, which I was sort of badly following some guides that I found online. But this time we're going to do it properly, and the first thing we need to do is we need to hydrolyze this. But the thing is, a lot of the fatty acids that will form from this are solids, which are hard to separate. So what we're going to do, since fatty acids are low melting solids most of the time, we're going to heat this up a bit before hydrolyzing, and hopefully the fatty acids will become liquid at that stage, and we can more easily separate them in the separatory funnel. So now that we have our mixture on mild stirring and with a hot plate temperature of 77 C, we can now begin to add a little bit of phosphoric acid. This is concentrated 85% phosphoric acid, and hopefully that should hydrolyze the components. into fatty acids and glycerol. And as you can see there, I might need to give that a little bit more stirring. And I had to give that a little bit more stirring speed, a lot in fact, in order to get the phosphoric acid to mix with the other parts of the mixture. I think that in a while that should hydrolyze and we should be ready to separate the components. I've added some more phosphoric acid and continued to stir the mixture for a while. And now I think it should be done. So we have our two layers in our separatory funnel, and now it's time to separate them. Here we will be saving the bottom glycerin layer, and the top fatty acid layer can be safely discarded. Now that we have separated the glycerol from the fatty acids, we need to neutralize the phosphoric acid. As you can see right now, when I put the pH paper in, you can see that our solution is strongly acidic. Now the easiest way for us to neutralize this phosphoric acid is to use a base such as baking soda, which you can commonly find online and in some stores. What I'm going to do now is I'm going to add this until the pH turns neutral. If you are using baking soda to neutralize or some other form of carbonate or bicarbonate, then it will foam quite a lot. So do be aware of this. Otherwise, if you add too much in a short amount of time, the foam could bubble over and cause a huge mess, and you'll lose a lot of your product. So now that we have a fairly neutral pH, what we can do now is boil off most of the liquid until the salts that formed during the workup precipitate. And once said salts precipitate, what we can do is we can add some ethanol to this to dilute it, as the salts won't be soluble in ethanol, and we can filter it off, and we can then redistill to form our final glycerol product. So that's just on a relatively high heat now, and medium-ish stirring, and I can't put my thermometer in there because the beaker is too small and it would just tip over. So I've put it at a reasonably high temperature, and hopefully the water that's there should boil off and we should be left with a kind of as a suspension of salts and glycerin, which we will dilute and then filter off and then redistill. So what we have here, after boiling off most of the water, is a gel-like substance that contains mostly two things, I imagine. The glycerin we have, and also a lot of phosphate salts. And so, because glycerin is actually quite soluble in alcohols as well as water, I have some denatured alcohol here, and hopefully when I add this, the glycerin will dissolve in the alcohol, and what will be left behind is the phosphate salts. So I'm just going to pour this in now. And I'm going to give that a bit of a stir. Okay, so after some stirring, the glycerin should have been taken up by the ethanol, and we can stop the stirring now, and we can filter off the salts that have precipitated out. So after filtering, I left this over a day, and I've now put it in my separating funnel, and we can see that well, it's hard to see on the camera, but I can see in real life that we have two layers here. Now what I think has happened to my favour is the glycerol has salted out from the ethanol water phosphate salt mixture. So what's happened here is, because phosphate salts and salts in general are quite soluble in water, and ethanol, what we added a little bit of prior also, is also quite soluble in water. But when you add a lot of salt, or when you saturate water with a lot of salt, any glycerol that's in there may precipitate out and form another layer. And I think that's what's happened here. And here we can see our glycerin inside of a beaker. It's quite viscous, and while it's not much, it does prove that we can definitely make glycerol from ethanol-derived biodiesel. And because I've proved I can make glycerol from vegetable oils, what that means is that if I can scale up this process, I can make more glycerol to use for future experiments and other uses. You can see it's quite a viscous liquid. It's more dense. It's actually one of the most dense organic liquids there are, which is quite interesting. Anyway, we made biodiesel from ethanol and methanol. I think the methanol one was a bit better. And also, in spite of the failure in extracting the glycerol and purifying it from my methanol batch of biodiesel, we actually made a tiny bit of glycerin from our ethanol batch. So with that, we move on to the final stage of this video, which is testing our biodiesels and comparing them against standard vegetable oil. So let's jump to that right now. So here comes the fun part, and this is the final testing of the biodiesels we have produced during this process. Now, as a control here, we have standard vegetable oil. We have our low-grade biodiesel here, which was our first batch that we made with methanol. We have our higher-grade biodiesel, which we also made with methanol, but we left it for a longer period of time for the reaction to occur. And here is the stuff we made using ethanol. And they're all in these cans here. No, this video is not sponsored by Pepsi. And they're just wicking up these fiberglass wicks, ready to be tested. Here is vegetable oil, and the vegetable oil doesn't really burn that well. There's quite a tiny flame, and it also took quite a while to get the flame going, which is probably because the oil isn't as flammable as the other fuels are, and just in general, I think because it's more viscous than the other fuels, it took a while to get up to actually wick up the wick. So yeah, that's our control using vegetable oil. So this is our low-grade methanol biodiesel, and you can see it already burns significantly better than our vegetable oil. And this is a good indication that we've at least made a form of biodiesel. So it's been about a couple of minutes now, and that is still burning, which I'm quite impressed with. Here's our high-grade biodiesel, also made using methanol, except this time we left the reaction going for an extra hour, and this increased the yield quite a bit. And as you can see, our high-grade biodiesel is burning quite brightly. And as you can see at the bottom, we also have a little bit of a blue flame, which means that this fuel is burning quite hot, in excess of a couple of thousands of degrees. Which is quite cool, considering we just made a fuel from oil and alcohol, basically. Certainly feels a bit warm. Perfect for a winter's day outside, as it is now. And just for a laugh, I thought I'd try and cook a sausage using this using this heater here. I don't think it's working very well. Oh, it's working a little bit. been burning. Our high quality methanol biodiesel has been burning now for over 10 minutes, let's say, and that is sort of a testament to the efficiency of the fuel. Now we have one fuel left to test, and that is the biodiesel I made using ethanol. So yeah, now here is the ethyl ester. So here is our ethyl ester. Unfortunately, I don't think this biodiesel is of that high quality, or high yield for that matter, and as you can evidently see, it's quite spitty as well, which indicates that because I left it for a while, I think it got a little bit wet. But anyway, it still burns a little bit better than the original vegetable oil, so I consider that a minor success. But I will, in the future, refine the process so that maybe we can produce a better ethanol-based biodiesel in the future. Anyway, that has been my own little personal project and investigation of producing biodiesel from a couple of different alcohols and under different conditions. And in the future I want to come back to this process again and try out different catalysts like lime, which is quite an interesting one because it is heterogeneous and so can be easily recycled from the biodiesel mixture, but that's for a future video. I hope you enjoyed watching this and watching my journey in this learning experience of making biodiesel and glycerin. And yeah, thank you very much for watching. Have a good Christmas, everyone, and I will see you next year. Take care. Bye for now. That's burning a little bit more stable now. Actually, coming back to this is burning more steadily now. I think it was just a bit wet. Anyway, take care and see you next time.